Okay, so we are starting chapter 8, which is hypothesis testing. So this is really the bulk of statistics. So the idea behind statistics is that we want to know if our sample is evidence enough to say that the mean is higher than what it actually is. Okay, so here's an example. Suppose a school superintendent reads an article which states that the overall mean score for the SAT is 910. Furthermore, suppose that for a sample of students, the average SAT scores in the superintendent's school district is 960. So it's higher. Okay, 960 is higher than 910. But is it significantly higher? Meaning, could it have been due to chance, or are they better than average? Okay, so that's what this. Can you conclude that? So you might say yes, but the means of your samples vary about the population mean when samples are selected from a specific population. So, is there a real difference, or simply due to chance? Is it a sampling error? Was it just happened to be that one day it was higher? Okay, so that's what we are determining in this chapter. So this chapter is all about how hypothesis testing works. There's several steps. Today we're focusing on the first two steps. Okay, so hypothesis testing is a decision-making process for evaluating claims about a population. There are two methods that we will cover, the traditional method and p-value method. The traditional method will be in 8.1, and the p-value method we'll talk about in 8.2. We go through 8.4 in this chapter. Also, this chapter, the test will be over just chapter 8, because we have to make sure that we know how to do hypothesis testing before we apply the hypothesis testing in chapter 9 and 10. So that's what we're focusing on for the next few weeks. And on your formula sheet, it has the traditional method on there. So you will have that on the test. Did you find it? Yeah. On the backside? Yeah. Or did you see it? Do you see it there? Traditional method. You have the 5 steps. So on the back of the chapter 13 stuff, there's 2 tables here, the traditional method and the p-value method. Okay, so the traditional method, the first step is that you're going to state your hypothesis and identify the claim. So you want to state what, we'll talk about the 2 hypotheses. You'll state the assumed hypothesis, and then we're going to state what we claim. So maybe I claim that our average is higher than the national average. Okay. Then we will find critical values from our appropriate table in Appendix A. So that means either the Z table or the T. So we'll find our Z sub alpha or our T sub alpha over 2. Then we'll compute a test value. So depending on what we're trying to find, we'll compute that value. So if it's a Z or a T, we'll compute that. So this process right here, you've done this before. Okay, that's what we did in chapter 6 and 7. And then the decision-making process happens. So after you found the critical value, you're going to compare your test value to the critical value. And you're going to make a decision to reject or to not reject the null hypothesis. And then after you do that, you'll summarize your results. This section is going to focus on steps 1 and 2. And we're going to talk about what everything means in this chapter, or in this section. So something to just kind of keep in mind is this is going to be different than anything we've done so far, okay? We're going to do, like, these 2 steps, we've done those steps, but the whole decision-making process, that's going to be slightly different. It's kind of like you're setting up an argument for whether you are true, whether your claim is true or not, okay? So that's the idea here. Okay, so step 1 is to state the hypothesis and identify the claim. So the statistical hypothesis is a conjecture about a population parameter. It may or may not be true. So a population parameter, remember parameters are like mu, sigma, so the population mean, the population standard deviation, population proportion, all of those are what you're making a conjecture about. And that may or may not be true. We have 2 types of statistical hypotheses that you are going to write each time. You'll have, the first one is called the null hypothesis, H naught. This is how you read that, H sub 0, H naught. That is going to state that there is no difference between a parameter and the specific value, or that there is no difference between 2 parameters. So you're assuming that in the case of the principal of that school, you're assuming that there is no actual difference between the 2 values, the 2 chains, right? And then the alternative hypothesis is H sub 1, so I call it H1. Yeah. So there. Okay. And that is going to state that there is a difference. So that could be that it's not equal to, that it's greater than, or that it's less than. So the alternative hypothesis states the existence of a difference between a parameter and a specific value, or that it states that there is a difference between 2 different parameters. So maybe a difference between 2 different proportions, 2 different whatever. We'll do more of this part in chapter 9. Second. Do we have any questions so far about what I'm talking about? Does it make sense at all? Yeah.
What's the, like, this H O and then H I, is that for like the sign for each of those?
So we're going to write down what our hypothesis is. So each time we'll write H naught, that's the H0, H naught, and we'll write H1, and then we'll write what our hypothesis is. Okay. So we'll practice that in just a second. Have you done any of this in, like, some of you IB or physics, you've done this? Biology? You've done the full, like, hypothesis testing?
Yeah. We need to leave chi-squared.
Huh, you just do chi-squared. Okay, so you kind of have a concept for what we're doing here. It'll be similar. Okay, are we done copying that down? Almost? Okay.
We also talked about psychology.
Mm-hmm. You don't do it in there? Okay. Are you an IB psych?
I was last year.
Okay. Is it a 2-year class or is it just
That's
one?
not HO.
So you can do 1 year or 2 years. Because this is definitely, psychology is going to use this whole process. Maybe it was your 2nd year that they might do that. I know they also do an ESS. Does anyone take that?
Yeah.
Huh? Or not E? Well, is that the environmental one? Do you do it in there? Have you done it there?
Are we done here?
No. I think you
We
might.
probably will.
I know the exercise one, that's the one I was thinking of. The exercise, the one that Coach Volker teaches. That one they do it. Because she comes up and asks me, yeah, she'll ask me questions about science all the time. Yeah, I don't know. Anyway. Okay, so we're going to do some examples here. So we're going to consider each of the following situations and we're going to identify our null and alternative hypothesis. So we're just doing the first step and really part of the first step because we're not going to identify a claim yet. Okay, so the null hypothesis is always that there is no difference, okay? And then the alternative hypothesis is always that there is some change, increase, decrease, okay? So will a new medication affect the pulse rate of patients? The mean pulse rate for the population under study is 82 beats per minute. So this is definitely something that when you do research in the medical field, you're going to do statistical tests. So is this medication helping these patients, or is it just due to chance that several patients had higher or lower, whatever it is? Okay, so our null hypothesis, our H naught, what parameter are we looking at? What does parameter mean? What'd you say?
New medicine.
A statistical parameter. Parameter. You have a question? No. So I mentioned it several times over here and was like that there is a difference between a parameter and a specific value. Parameter.
Is it like a? It's like a in between.
No. What'd you say? Mean is a parameter. Like population mean is a parameter. Population standard deviation is a parameter. When we find a sample mean, that's called a statistic. Okay, so that's something that we've seen and we'll still use that information here. So the parameter for this is what? What is it standard deviation? Is it
pulse rate?
Mean. Okay, so our parameter is the mean. And what do we use for parameter? What symbol? For mean? Mu. Okay. Okay, so mu is my parameter. So mu, what we are assuming is that it's not going to affect it. Okay, so that it's going to stay the same. So mu equals 82. That is our null hypothesis. Okay, now the question is, will it affect the pulse rate? Does it specify that we want it to go up or go down or just be different? Different. Just be different. Okay, so our alternative hypothesis is that it's not equal to 82. So it's just different. This would be a two-tailed test because you have two options. be greater, it could be less than. Okay? All right, let's try another one. That's it. We're only doing step one. So we're just practicing the finding the hypothesis. Okay? The mean life of an automobile battery is 36 months. A chemist creates an additive with the hope of increasing battery life. Okay, what is my parameter? Mu. And what are we assuming? What'd you say? Okay, so mu is equal to 36. So we're assuming that it's 36. What is my alternative hypothesis? Yes. So I am wanting to show that the additive will increase the battery life. So mu is going to be greater than 36. So this would be a right tail test because it's just the greater than. Okay. All right, here's another one. The mean monthly heating bill for homes is $78. A contractor develops a new type of insulation to lower heating costs. What is my parameter? Mu equals 78. And what is my alternative hypothesis? Right. So we want to decrease, reduce that, so less than 78. That would be a left tail test because it's on the left side, less than, lower in cost. All right. So important note. The statistical evidence can only be used to support the claim if it is in the alternative hypothesis or to reject the claim if it is the null hypothesis. So that can get confusing. So I'm going to explain that a few times, most likely every day. That was good. Yeah. Because we'll talk about it every time we do a hypothesis test, okay? So what this is saying is that I have an H naught, and that's the assumption, like it's 82, okay? I cannot prove that that is true. I can't prove that that is true, but I can reject it. I can find evidence to support that it's not that, but I can't say that it is that. Okay? If my claim is in the alternative hypothesis, I can find evidence to support that claim, that it is different, but I can never know for sure, so I can't prove it. Because even with confidence intervals, we had 90% confidence, 95% confidence, 99% confidence. We can't ever be sure that it's not due to chance. So we always find evidence to support a claim or to reject the hypothesis. And then these, there's some keywords for greater than, less than, not equal to. So you can see those in the book, or you can go back and look at those in the notes if you want to write them all down now. So higher than, above, longer than, bigger than, not equal to, different from, has changed from, all of these, okay? Do I have questions about this right now? I'll continue to say it, so a few more times today. Okay, so now you're going to do it, what we just did. So the alternative hypothesis and the null hypothesis. You're going to state what they are. you could write them on a whiteboard, then it's easier for me to see that. You just write your 2 hypotheses on a whiteboard, and I'll hold them up. Yeah, just a marker.
Yeah.
Ready? Sorry. Huh? I didn't want to hit him. So I aimed short. So we're always going to have, I know that so that's a way to do it, okay? But we're always going to do equal for the null, and then we'll have like greater than or something in the greater than or less than or not equals to. Okay. So what is my null hypothesis? U equals 30. And we are thinking that those who gamble spend more than $30 a day. So this would be greater than 30. Okay. Questions about that? Okay, try that one. Alternative hypothesis. I like alternative hypothesis. Yeah. Yeah. Good. So our H naught is mu equals 120, but then we are wanting to lower that, so it's going to be less than 120. Okay. One more like this. Can you turn it around for me? Second one. Good. Okay, so, they're replacing the physical textbook with online version may change the student's score on the final exam. Are we assuming that it's going up or going down? No, just that it's going to change. So we have mu equals 83, and then mu is not equals 83. Okay. You can put your whiteboard away if you would like. Okay, so I already mentioned this. When you have a not equal to, that's a two-tailed test. When it's a greater than, it's a right-tailed. If it's left-tailed, you're going to have a less than sign. So we'll be referencing that. So the researcher is typically wanting to support their claim. So that's why our claim is usually listed as the alternative hypothesis. Because remember, we can only reject the null or find evidence to support the alternative. So reject the null. So if we want to reject our claim, we can put it up there. But usually it'll be the alternative hypothesis because we want to support it. All right, so now we're going on to step 2, and that is finding the critical values. Oh, just kidding. All right. Yeah, okay, we should talk about that. Okay, so there's two possibilities. The null hypothesis is true, and the difference between the sample mean and the population mean is due to chance. Okay, so if the null hypothesis says that the actual money they spend is $30, so it's equal to 30, and we have a sample and that's different than the population, that's due to chance. That it's not actually because they did better. The second option is that the null hypothesis is false, and the sample came from a population whose mean is not the value, and the population mean is unknown. So that they did better, or they did worse, or they did whatever is assumed, okay? So this chart kind of may look confusing, but we think of the normal curve. Remember that the area under the curve is a probability, okay? So the probability that the mean will fall in this area right here is much higher. Okay, but if it falls out here in one of the tails, that means that it's much more unlikely that it will fall there. So it's not just due to chance, because it's unlikely to fall in the tails. So that's how we decide whether we're going to reject or not reject each time. Okay, if it's actually different or if it's due to chance. So there is still a chance that something over here could happen. It just may be like less than 1%. Okay? All right, so now, step 2. We're going to find the critical value. So a statistical test uses the data obtained from a sample to decide whether the null hypothesis should be rejected. So you're going to take a sample, and then we call this a statistical test, whatever thing you run. So your test value or your test statistic is the numerical value obtained from the statistical test. So you decide whether you're going to do a z-test or a t-test or chi-squared or whatever it is that you're going to do. There's all these different types of t-tests and z-tests and statistical tests in general. Okay? And all of those are determined by how you're sampling. So are you sampling and comparing two different groups? Are you comparing one group to the population? And this is where your project will come in. You'll come up with a situation and you'll have to decide what kind of test you'll do. So our decision will be made based on the critical value and then our test statistic, whatever is found. If the difference is significant, then the null hypothesis will be rejected. If not, it's not rejected. But since we're using sample data, we talked about this in the beginning of the very beginning of the year. Sampling, you could have a sampling error, right? So I try to get the best sample that I can, but there's always a chance of a mistake. Okay? You could have an anomaly, group of people that all have very similar interests or whatever it is. So there are possibilities of errors. Okay? So once a decision is made whether to not reject or reject the null hypothesis, there are 4 outcomes that are possible. Okay? The first one is called type 1 error. This says that we reject the null when it is true. Type 1 error. So what that means is, in the case earlier we said about the pulse rate, it was like, will a new medication affect the pulse rate of the patients? The mean pulse rate was 82. So if we made a type 1 error, that means that it might not actually change the pulse rate, but in our sample it did due to chance. So we rejected the null, but it was true. The second outcome that's possible is we reject the null when it's false. So that's a correct decision. The third one is that we do not reject the null when it is true. So the null is true, and so we didn't reject it. So that's another correct decision. So we're always going to either reject or not reject the null. Those are our 2 options. And then the fourth one is called a type 2 error. We do not reject the null hypothesis when it is false. So you have a null hypothesis that is false, but you didn't reject it. So that the pulse rate one, it would be like that the medicine might not change in the sample, but it would in the population. So that means that you may be putting out a medicine that you're not trying to change the pulse rate, and it didn't in the sample, but it does when you put it in the population. So would that be good? No. Okay. So now consider a jury trial. So same 4 outcomes, a jury trial. What do we always assume? Innocent. Innocent until proven guilty. So your H0 is that they're innocent. Your H1 is that they are not innocent or they're guilty. Okay. What would a type 1 error be? Reject the null when it is true. So H naught was innocent. H1 was guilty.
So they're guilty in the lot. So like you say they're guilty when they're really.
Okay, so rejecting the null would be that you're here, that they're guilty, but this is true. Right? So you said it right. You said it right. Yeah. So this is true, that they are innocent, but you said they were guilty. Okay? So what is number 4? Yeah. So this is false, but we didn't reject, we do not reject the null when it is false. So this is false, this is true, but we didn't reject it. So we said it's innocent, but they were actually guilty. So those are your 2 types of errors. So that might help you when thinking about the error. That's just a table version of that. And we already talked about that one. Okay. So now we use Greek letters for each type of error. The level of significance is the maximum probability of committing a type 1 error. And that's going to be alpha. So the probability of a type 1 error is alpha. The other thing to keep in mind with the type 1 error and type 2 error in the jury trial, do they ever really know for certain one way or the other? Like the jury, they're given evidence, right? And their evidence, unless someone is like, I did it. Their evidence is there enough evidence to support this claim that they are innocent? Or is there enough evidence to commit them to jail or whatever, that they actually did commit the crime? So you're never actually proving that that was true. Okay? So you're never proving that they were innocent, because there's always going to be some, probability that they could have done it, unless you have, like, when they confessed or whatever. So that's how people, there are errors. That's how people go to jail that aren't supposed to. That's how people get let out when they're not supposed to. Okay? So you're never proving something. So keep that in mind when we're doing the statistical test as well. Additionally, we have a type 2 error is going to be beta, but it is typically easier to compute alpha. So that's what we use. So the alpha that we've been using is still, you're going to think about it the same way. Okay? Alpha is going to be a probability, and that's going to be the probability in the tails, that type of thing. Our agreed upon significant levels are 0.1, 0.05, and 0.01. So that would be 90% confident, 95% confident, 99% confident. Those are still the same agreed upon levels. So it'll be do a hypothesis test at an alpha equals 0.1. Okay? So that's setting the level. This is the probability of committing a type 1 error. Okay? Type 1, again, was rejecting the null when it is true. So you rejected that they're innocent and they went to jail. Sounds pretty bad, right? You don't want to go to jail for a long time when you're innocent. So you want that to be small. Okay? So alpha is 0.1, 0.05, or 0.01. Just depends on how bad it is for you to make that error. Okay? Okay. We're gonna do this last slide. Okay. And then we'll finish the rest of the notes. They're shorter. We'll finish those at the beginning Friday. Okay, so the researcher decides what level of significance is appropriate depending upon the seriousness of the type 1 error. So I just said that. So then we consult the appropriate table to find your critical value. So how bad is it if I make a type 1 error? So is it going to affect the health of someone? Then it'd be pretty bad if I made that type 1 error. So I'd want my alpha to be very small. If it's not as serious to make that error, I'm just talking about behavior or something like that, then you can have a bigger alpha. So then, once you have your alpha, you find your z sub alpha over 2 or your z sub alpha, depending on the type of test you have. If you have a two-tailed or one-tailed. And then you're going to have a critical or rejection region. So that's going to be the part, like we'll shade it and say that there is a significant difference and the null should be rejected. And that will make more sense when we actually do a hypothesis test. But I want you to have it down so you can reference what I'm talking about. So we would have our curve, and if our alpha is over here, this is the area that if my test statistic falls in that area, I reject it. So that's called the critical region or the rejection region. So then the non-critical or non-rejection region is the other part. So if my value lies anywhere over there, then I don't reject H naught. So the range of test values that indicate that the difference was probably due to chance. So it's more probable that it's happening over here. So then the hypothesis should not be rejected because it could be just due to chance. And the last one is the critical value. Separates the critical region from the non-critical region. So this is your, whatever you choose your alpha to be, that's your Z or your T, whatever it is. That's the value that's separating the two regions. And then your test statistic falls in either region. That's just a picture. So this is your critical value. This is the critical region. This is the non-critical region. The 0.01 is your alpha. The other one's alpha minus 1.
Right.